thanks for the introduction and for you being here. And I mean, of course, it's an honor and a huge pleasure to be part of this program. So, right. So I'm a differential geometer, and I'm going to actually talk about something that very directly relates to the last sort of part of the previous talk about sort of 2A and M theory duality and how sort of G2 holonomy matrix arise from kind of 2A solutions of a certain kind. So the perspective that I'll discuss is the one of a differential geometer. So we're interested in actually sort of making this correspondence sort of rigorous from a mathematical point of view. So what I'll discuss is joint work with Mark Haskins and Johannes Nordström. So the for most of the talk, I'll review work that we've done a few years ago, and then towards the end, I'll discuss some new results. So I apologize to those of you who have heard the first part of the story elsewhere. So, all right. So, okay. So the starting point is kind of making progress at a mathematical level of what Jacob was describing earlier. So, so this fact that sort of certain solutions of type 2A are sort of have a M theory uplift to G2 holonomy matrix. So recall we're sort of a real six-dimensional manifold with an SU3 structure. So for me, little omega is the sort of non-degenerate 2 form. So what was J in the previous talk? Capital omega is a complex volume form. And the sort of complex volume form determines the almost complex structure J. And sort of these couple of forms, they satisfy some algebraic constraints. The first one says that little omega wedge capital omega is 0, or in other words, little omega is a 1,1 with respect to J. So I can use J and little. And then the fact that we're dealing with SU3 structure is this sort of constraint. So the volume form induced by the sort of Hermitian form and the volume form, real volume form coming from the complex volume form are the same. Sorry? No. So for now is just this, and actually the equations that we want to impose are the following. So we have this 6 manifold with an SU3 structure. We have a positive function, and we have a 2 form, which is a Raman-Raman's 2 form flux, and these sort of special instance of the 2A system where almost everything is set to 0 except this 2 form flux is something like this. So up to conformal rescaling, we actually have the non-degenerate 2 form is closed. So we have a symplectic structure. Sort of half of the complex volume form is closed after rescaling, but then sort of this is saying that we're not even looking at integrable complex structures. We have some sort of symplectic manifold with an almost complex structure satisfying special constraint. And then this 2 form kappa is closed, at least for now. Okay, so how do we get G2 holonomy metric in 7 dimension? Is this observation that if the cohomology class of this closed 2 form is actually integral, then automatically there is a 7 manifold, which is simply a principal circle bundle over this 6 manifold B. And there's a connection 1 form on this principal circle bundle with curvature precisely kappa. And then we have all the data to write down a circle invariant G2 structure, so a three-form, non-degenerate sort of three-form on the total space of this principal circle bundle. The induced metric looks something like this, where G is the metric induced by the SU3 structure on B, and then we have sort of circle fibers and these sort of positive functions, basically the length of the circle fibers. And then this system of equation is exactly the condition that this G2 structure is closed and co-closed, and therefore the holonomy of this induced metric is actually contained inside G2. Right, this is stuff that you all know is got back. So the metric G phi is, so here phi is a G2 structure, so it's a three-form that is sort of positive definite or something, so just by linear algebra is going to define a Riemannian metric. So at every point, the stabilizer of this three-form is G2, and since G2 is inside SO7, there's naturally a Riemannian metric associated to it. And, a bit like precisely in this context, sort of out of the kind of SU3 structure, we had a metric in 6 dimensions. All right, and then I guess there's a natural parameter that you can add here, which would be the string coupling constant in 2A, and it's just related to the size of this circle. So I can add that parameter epsilon that's measuring sort of the some overall kind of size of the circle fibers. And then as a geometry, one idea would be, can we produce G2 holonomy metric starting from, so sort of the observation, sorry, is that if you now, so these are the equations, so these two remain the same, and then the third equation, when we introduce this parameter epsilon, gets the form like this. So if I just take the limit epsilon equals 0, I do get just the equation that gives me a Calabi-Yau structure in 6 dimensions. So when the circles are collapsing to points, then I just get a Calabi-Yau structure, of course. And then one sort of aspiration would be to, can we produce G2 holonomy metric starting from Calabi-Yau 3-4 plus extra data? Well, at this point, there's no reason. So I can always choose it positive by changing kappa into minus kappa. Yes, at this point, sure. There's no. I'm just taking positive in the sense that is the square root of the length of some kind of mean value of the length of the. But I mean, yeah, you're right. It's. Yeah, but then I mean, notoriously, sort of, we don't really have methods to produce G2 holonomy metric unless we are sort of close to a solution. So basically, using the parameter epsilon small gives you a potentially sort of a new way of producing G2 holonomy metrics. Okay. No, this is just a sort of kind of the solutions to this system will depend on epsilon and. Huh? The initial data, yeah. Okay, so first of all, as the story that I told sort of is kind of, it's just a sort of some sort of cartoon at this point, and this is also well understood in physics, so because there are no compact solutions of this 2A system, for example, if we have this interpretation in terms of G2 holonomy metric, then since G2 holonomy metric are Ricci flat, then S1 invariant compact Ricci flat metrics, they're necessarily products of a circle times something lower dimensional. So we need to allow sort of kind of some source of non-compactness, and there's 2 ways that we can do this, and we can also take them together. So one way is just to say, let's look for complete non-compact examples, so sort of local examples. and another one will be to introduce singularities. So for the kind of non-compact examples, then so recall. So what I said, we want to start with a Calabi-Yau threefold. So we need to start with a now non-compact Calabi-Yau threefold and a very large class, very well understood class of non-compact Calabi-Yau threefolds is the one of asymptotically conical Calabi-Yau threefolds. So these are sort of complete metrics that are asymptotic at infinity to a cone over Sasaki-Einstein flat manifold link. That sort of they're smooth, sort of smooth, but non-compact at infinity. Right, and sort of, I mean, there's a very well-developed theory of this existence and uniqueness result by many authors. The sort of kind of final sort of statements on this existence theory for asymptotically conical Calabi-Yau metrics is due to work of Conlon and Pine, but the work starts from, I don't know, Tian Miao in the 90s, etc. Okay, so right, so now we're non-compact, so we can imagine doing what I was proposing before. So we start with a principal circle bundle over one of these Calabi-Yau, and we look for G2 holonomy matrix, and then so the G2 manifolds that you arise from some sort of version of the story that I was saying on this non-compact, starting from an asymptotically conical Calabi-Yau, would be precisely this class of metrics that are sort of we're calling ALC, asymptotically conical. So metrics that at infinity look like a kind of a circle times a cone, or not really a product, but sort of some Riemannian submersion over a cone with fibers that have some fixed finite length. Okay, and where this is so this symbol stands for asymptotic at infinity, and then really you might want to include some sort of polynomial decay, which is natural when you look at things asymptotic to cones. Okay, and I mean, there's definitely example of this known sort of more than 20 years ago, where basically a lot of activity in the theoretical physics literature has been done around these ideas, and sort of in particular, there was the very first example was an explicit example of a ALC G2 metric on S3 times R4, and then lots of various other families sort of conjecture based on numerical experiments and other type of considerations. Okay, and then so we are saying sort of this will be one possibility of kind of trying to implement this strategy of producing G2 metrics from Calabi-Yau with sort of on some sort of circle vibration over Calabi-Yau. So the other possibility is introduce singularities, and this will be sort of the physics side of the story. Just will be branes wrapped along special arrangements of manifolds inside the Calabi-Yau. And there's two relevant type of branes here: D6 branes that up in M theory live to basically geometry that's locally R3 times the tau naught metric, where R3 is basically the tangent space to the special Lagrangian, and orientifold planes, which are modeled instead on R3 times the Atiyah-Hitchin metric. So eventually, sort of if you throw in these singularities, then you can imagine, as Jacob was discussing, sort of actually producing compact G2 holonomy metrics by this procedure. So this is the ultimate goal of the work that I, with Mark Haskins and Johannes Notion, that I'm presenting. As a lower dimensional story, a few years ago, I did give a rigorous construction of Haber-Kellem metrics on the K3 manifold close to a limit where they become three-dimensional, so T3 times Z2, and basically the construction is what Jacob was outlining. So one start with some sort of Gibbons-Hawking ansatz on T3, which is Z2 invariant. So give some S1 invariant hyperkähler matrix, and with some D6 brane and orientifolds, and then near the orientifolds, one needs to glue in some copies of the ALC manifold, then sort of prove that nearby this approximate hyperkähler metric, there is going to be an actual Ricci flat metric. Okay. Right. So okay. So the sort of maybe our sort of ultimate goal will be to produce something similar for compact G2 manifolds, but what we can do right now is more in this sort of non-compact setting. Okay, so so I'm now going to describe some of our results in this non-compact setting, and the first result is where we have a smooth asymptotically conical Calabi-Yau threefold, so smooth but non-compact. I have a cohomology, integral cohomology class, so I have a circle bundle, and I want to look for basically 2A solutions with so basically we're looking at 2A with Ramond two-form fluxes in this non-compact situation. We want to prove existence of G2 holonomy metrics that live on this circle bundle M, and where the circle fibers are very small. Okay, so there's a necessary conditions for this to satisfy that the sort of first-gen class of the circle bundle wedges 0 with the Kähler class of the Calabi-Yau, and that sort of comes out naturally by solving the equation. Is also, I think, as an interpretation in terms of a sort of vanishing of the superpotential and the first derivative. So yeah, omega, so sorry, here there's a typo, this should be omega 0. Omega is, yes. Yeah. Okay, so, and basically the theorem is a very general existence result. So whenever we're given an asymptotically conical Calabi-Yau threefold, cohomology class in degree 2 that satisfies this condition, where omega is the Kähler class, then for epsilon sufficiently small, there is a one-parameter family of these ALC G2 metrics on this principal circle bundle that in the limit epsilon equals 0 just converge back to the asymptotically conical Calabi-Yau. Okay, so okay, so the proof involves some analysis, but let me just instead explain what sort of so this is a general existence result, and what sort of things you can get out of these results. So, for example, so first case, you can apply this to the small resolution of the conifold. Since it's a small resolution, the fourth cohomology is just 0, so this condition is vacuous. And then this reproduces one of these family of ALC G2 metrics that were conjectured in the physics literature in the early 2000s. Another thing that you can do, you can take the canonical line bundle of P1 times P1. So this is a Trepan resolution of Z2 quotient of the conifold. Now you have sort of lots of different choices of circle bundle depending on 2 integers, and as long as these 2 integers are positive, then you can always find a Kähler class so that this condition is satisfied. So then you take this data, apply our theorem. This gives you infinitely many of these ALC G2 manifolds. But you can do even more. So if you now take, for example, small resolutions of certain compound P singularities, which are sort of well-studied Calabi-Yau cones, and then asymptotically conical Calabi-Yaus asymptotic to those, then you get infinitely many, as this integer P varies, it gets infinitely many examples with arbitrarily large second and third Betti numbers, and G2 holonomy metrics then depend on an arbitrarily large number of parameters. You can even sort of by an extension of this theorem that I developed where you allow the Calabi-Yau to be an orbifold, then you can take sort of orbifold partial resolutions of YPQ cones that are orbifolds, and that gives you infinitely many different families of G2 metrics on S3 times R4, just asymptotic to different circle bundles over different Calabi-Yau cones. And then in a physics paper with Bobby Acharya, Marwan Najjar, and Eric Svanes, we studied more sort of Kreppel resolution of hyperconifolds. That is what this condition gives you, and thinking of the physics of these as jewels to a theory on some sort of T star over some length space with brains, etc. Okay, so if there's no question, I'll move on. So what sort of yeah, these are a list of examples. So you want to, so maybe, I don't know, maybe because, so I can do this CAP singularity is the easiest to write down. So is, so the Calabi-Yau cone that you start with is something like this. So when P is 1, this gives you just the conifold. And when P is higher than 1, then these are these certain kind of compound AP singularities. And so when you start with the complex data of something singular like this, so there's two questions. So one question is, does this emit Calabi-Yau cone metrics? So does the link of this has a Sasaki-Einstein metric? This is a hard question, and this was sort of to prove that this example do have Calabi-Yau cone metrics actually comes from work of Collins and Zekheidi on sort of K-stability and existence of Keller-Einstein, in this case, conical Keller-Ritchie flat metrics. And then you want to sort of, once you have this, to get asymptotically conical Calabi-Yau, you want to start looking. So in the context of this theorem, another thing to do is look for sort of Kreppel resolutions of these. And this particular example are good because sort of there's papers from the 80s in the sort of algebraic geometry literature where they study sort of isolated singularity that admit small resolutions, and small resolutions are sort of useful for us because then the fourth cohomology is just 0, and we don't need to check anything. So no, so this was I'm saying, I put this here because sort of when you take this small resolution of the YPQ cone is explicit, the small resolution is an orbifold. It also has an explicit asymptotically conical Calabi-Yau metric that was written down by Martelli and Sparks. Don't remember exactly when, earlier than this, 2004. Using some special ansatz that in Keller geometry that's called Hamiltonian two-fold ansatz. So the way you write a sort of explicit Calabi-Yau metric, and then the G2 holonomy metric is not explicit as far as I know. It follows from the existence of this G2 matrix follows from this theorem, or rather an extension of this theorem where you allow the Calabi-Yau to be an orbifold. So as far as I know, this is not explicit. It's just proved by sort of solving the equation, proving that So you can solve the equation when epsilon is sufficiently small. Any other questions? Okay, so right, so the next so yeah. No, to all order in epsilon. Well, because I mean, epsilon must be small in the sense that I'm solving the nonlinear equation to all order in epsilon, but I'm solving by sort of perturbation of the solution at epsilon equals 0, which is the Calabi-Yau. So I'm saying that, so I'm applying the implicit function theorem, saying near this solution at epsilon equals 0, there exists solution for all epsilon positive, but the epsilon must be. Yeah, for each fixed epsilon, I fix epsilon, there is a metric that is really Ricci flat holonomic G2. Solves fully the nonlinear equation, right? And I have one for each epsilon that's sufficiently small depending on the data of the Calabi-Yau that I start with. No. Right. Okay, but that's precisely sort of the next step that we took up. So kind of how small epsilon could be, how big we can make epsilon, right? And now, in general, there's no way that we can answer that question in G2 geometry because all that we can do is find a G2 holonomy metric. Yeah. Yeah. So there is so when I say I'm starting with an asymptotically conical Calabi-Yau, so I fix the resolution parameter, and then for a fixed resolution parameter, there exists an epsilon 0 that depends on the resolution parameter, such that I have a G2 holonomy metric for all epsilon less than that epsilon 0. Sure. Sure. So by here, we're doing just locally around, if you want, around a sort of point in the interior of some moduli space of Calabi-Yau. And I'm just thickening a bit into sort of, in theory, the modular space. Yeah, that's what's happening. Okay, but precisely as, I mean, of course, it's a very interesting question to precisely go to a limit where precisely either this epsilon grows and how much it grows, or equivalently by rescaling, what if I move the Calabi-Yau moduli towards a singular Calabi-Yau? That's right. So that's the next question. And what I wanted to say, sort of doing it analytically in general, it's out of question at the moment. We just don't have enough understanding of G2 metrics to be able to do that. Even for Calabi-Yau, sort of limits starting variable degeneration of Calabi-Yau metrics. I mean, this is only something that happens in the last few years, despite, of course, existence of Calabi-Yau metrics is known since late 70s by work of Professor Yao. So, okay, so in general, it will be impossible, but we can restrict to examples, which is also what was done in physics literature in the early 2000s that have lots of symmetries. And then what can we say there? So, so here, just wanted to recall the tau metric on R4. If you introduce this parameter epsilon, it's very explicit. Sort of epsilon goes to 0, you're kind of collapsing down to R3 with D6 brane at the origin or curvature concentration at the origin. And as epsilon goes to infinity, sort of the circles opens up and you have just a flat metric on R4 that you can look at this like this, and then again in this physics work, sort of there was this one explicit example on S3 times R4 of ALC G2 metric, but sort of then numerically a whole family, kind of where the parameter is precisely this epsilon. So epsilon goes to 0. This was corresponding to sort of collapse to the deformed conifold with the 6 brane wrapped in the 0 section here. And epsilon goes to infinity. Again, the circle, the conjecture, sort of the expectation was that the circle opens up and you get asymptotically conical G2 metric that is also known from the late 80s. Is the Brand-Salomon metric on S3 times R4. Right, so the second main result that I want to present is that we managed to understand this completely and in a sort of mathematically rigorous way for all the examples that have a symmetry SU2 times SU2 times U1. So what are these examples? So there's the sort of two families, B7 and B7, that were already considered in the physics literature. So these live on S3 times R4. The sort of moduli of the G2 structure depends on two parameters, epsilon and lambda. So the epsilon is this size of the circle at infinity, if you want, and the lambda is basically the diameter of the S3 at the core of this space. So some, and then basically, I mean, you can rescale. So really, what matters is more the ratio of these two parameters. And as I said, when this ratio goes to 0 is what was covered by the previous theorem. But now what does happen when this ratio goes to infinity? And there's two ways of studying the limit. So one way, if I fix lambda to be some non-zero value and I let epsilon go to infinity. So the circle is opening up and I get this asymptotically conical G2 metric, the Brand-Salomon metric on S3 times R4. But then what we discovered is that there's another useful way of taking this limit where instead I fix epsilon and then lambda goes to 0. So that's precisely sort of going to a limit where I'm sort of moving in the module of the underlying Calabi-Yau towards a singular point. And then what we found is actually a new G2 metric on as a manifold. This is sort of the cone over S3 times S3, so S3 times S3 times radius parameter. But the metric is not a cone. The metric is at infinity as this ALC behavior with some fixed epsilon, so some circle bundle over the conifold. But then inside, there's a codimension 7 isolated singularity of the G2 metric that is modeled on the Brand-Salomon cone over S3 times S3. So we can sort of these two cases. So okay, where sort of this sort of conically singular LC G2 space doesn't seem to have been sort of kind of imagined in the physics literature. But then also we can apply the same kind of study to these infinitely many families that arise from circle bundles over the canonical length bundle of P1 times P1. So these are parameterized by two integers. And then again, when epsilon goes to 0, you have this collapse to the Calabi-Yau. And when the ratio goes to infinity, if you fix lambda and let epsilon go, if you let me first fix epsilon and let lambda go to 0, then I'm just recovering Z2 quotient of this previous example. But if you now fix lambda and let epsilon goes to infinity, so you get new asymptotically conical G2 metrics. And in this way, these asymptotically conical G2 metrics depend on M and N. So we actually this way produced infinitely many asymptotically conical G2 metrics, while before this theorem there were 3, 4, 7. Yeah. is an existence proof, starting sort of because of the symmetry you reduce to some ODEs, and then we prove that there exists solutions of the ODEs with certain behavior at infinity. Yeah, and I mean, in the physics literature, I guess some of the ODE systems were studied numerically, so except for this one explicit Branduber, Gomes-Guber Gukov metric on S3 times R4, no other closed form expression for this metric was found. Okay, so in particular, sort of this story, I mean, as a kind of Riemannian geometry and differential geometry gives a kind of realization at the level of metrics of the M-theory flop that was studied by Atiyah, Maldacena, and Baffa, and Acharya. So basically, sort of the first part of this theorem. So you have these three families of metrics. Sort of, if I go along one of these branches, I collapse down to some Calabi-Yau, some solution of 2A, here the form conifold with the sixth brane, here sort of resolved conifold with Raman two-form fluxes, and then in the middle you have kind of a common vertex that can be described kind of in these two different ways, either this Brans-Hahn metric or this singular ALC G2 metric. And then sort of same story here, but now we have many branches depending on how many ways I can write n plus n as n and n. Right, and the sort of qualitative picture is precisely the same. Yeah. Well, but then sort of I mean, if MNN are not co-prime, then sort of the manifolds are just finite quotients of other ones, and so you might. But I mean, it's still there's a. Okay. Right. So this is kind of our work of a few years ago, and now I want to come to sort of more recent stuff that hopefully is that is going to appear in arXiv in a few weeks. I have no idea. I have no idea where this came from. I think, or rather, it came from because the first ALC matrix, I mean, I might be saying something wrong, but I think the first sort of special holonomy matrix with this ALC type asymptotics were certain spin 7 metrics on manifolds that I think were called A8. Then I think out of that, then this labeling came around, but I'm not sure where the significance. No, yeah, nothing to do with that. All right, so okay, so far we were describing mostly just non-compact geometries with Raman, I mean 2A with Raman fluxes, or in one example 2A with the sixth brane. But we know that if eventually we want to think about compact examples, then we are going to need some manifolds because of tadpole cancellation. So what can we say about models for G2 metrics that can we think of sort of M-theory uplift of manifolds? So first of all, the Atiyah-Hitchin metric is playing a role, is a lower dimensional example. So the Atiyah-Hitchin metric is a Haber-Kelln matrix that lives on CP2 minus RP2. And it's not a circle bundle, but sort of it is asymptotic with exponential decay to a Z2 quotient of a circle bundle over R3. And crucially, the sort of charge of the circle bundle is negative. And that's why There's two options. There's the non-simply connected version that would have charge -4, or the simply connected one that I'm considering here, charge -2. Both, I mean, will play a role. So, and again, in this physics works in the early 2000s, there's a predicted extra family called A7 for reasons that I'm not sure about. That is kind of supposed to be some sort of kind of M-theory uplift of orientifold wrapped on the three sphere of a deformed conifold. Okay, and this would be an example of, at infinity, again, it will be a Z2 quotient of a circle bundle over a Calabi-Yau cone. So by analogy with what happens in four-dimensional hyperkähler geometry, we decided to call metrics like this dihedral ALC G2 metric. So here is a circle vibration that is not a circle action. That's this involution Z2 that acts as a orientation reversing involution of the circles. I'll explain in a moment. Okay, so so the new theorem is about producing this family, at least in a limit, rigorously. So so we produce this one parameter family of this dihedral ALC G2 matrix, and the way we produce them is using some of these building blocks that we have from here. So this singular LC G2 matrix and this asymptotically conical G2 matrix. So what you can do is the following. So you start with the singular ALC G2 metric, which is this, so at infinity is a circle over conifold, but inside it has a codimension 7 singularity. So what are the symmetries of this? Well, there's this SU2 square, and then there's N is this normalizer of U1 inside a third copy of SU2. So inside this N, there's two different finite subgroup, Z4, sort of one that sits inside kind of the circle inside this normalizer N, and the other one is a dihedral sort of Z4 inside the normalizer. So this Z4 inside it has a Z2 that's sort of acting by orientation reversing of the circles at infinity. Okay, so you start with the singular thing, you quotient, right? And then if you quotient by this cyclic Z4, you can use the asymptotically conical metric. Oops, sorry. So this can be, so this is now so sort of as a codimension 7 singularity at infinity, some circle bundle over the Calabi-Yau cone, and here you can desingularize using this new asymptotically conical G2 metric on the space M11, this corresponding to choice M and N both equal to 1. Okay, so this produces, basically, this will give you back the metrics that we knew before from the previous theorem. But now you can do another thing. So you divide instead by this Z4 dihedral. And then you observe that when you look sort of close to the singularity, actually, since the symmetries of the singularities are actually, it's a larger group, is SU2 cube, then actually this Z4 dihedral is conjugate inside this larger group to Z4 cyclic. So this means that even if you started sort of the difference of the two groups, you only see it from infinity. When you're down here, the two groups are the same, so you can still use this M11 to the singularize. Okay, so this gives you sort of some of these. So then the theorem is basically, again, you start with some approximate G2 holonomy matrix, and you need to prove that nearby there exists a true solution. Okay, so this gives this A7 matrix. So this is in a limit where you're close to having these isolated singularities. So it's more like a what would be strong coupling limit of this 2A with orientive 2A on the form conifold with an orientifold on the zero section. Yeah, I mean, the singularity is already there. It creates a new singularity that is just a quotient of the previous one. Yeah. So, I mean, it's something that one needs to prove. There's some topological, in general, there's some topological obstructions that needs to be satisfied, but they are in this space. Yeah, so behind here, there's a theorem that says that you can always desingularize under certain conditions. No, again. No, but again, I'm not sure how much one could hope for a. We didn't look for an explicit things, but certainly I would imagine that sort of groups of physicists that looked at these ALC G2 matrices in the early 2000s, they were definitely looking for explicit example, and yet they found just one. I mean, just sort of specific parameter value, the specific tuning of the parameters within this old family. Right? So I don't know how one should be. I mean, this is not a proof, but that's life, correct? That's life, but luckily some analysis helps you to understand also things that are not explicit. No, here. So I'll kind of close just with two sort of. So this is more or less the sort of existence result that we have for now. There's of course many more things that one could do. There's a sort of some analytic existence result for when you have an arbitrary Calabi-Yau with the 6 branes and orientifolds, then eventually sort of compact example. We'll see how much time that will take us. But I'll just sort of comment two extra sort of in the paper that's going to come out soon. There's a bunch of extra results. So, for example, construction of moduli spaces of these ALC G2 matrix, uniqueness results for kind of invariant G2 matrix that are asymptotics to this model. So basically, the only complete ALC G2 holonomy matrix that are asymptotic at infinity to this must be this. So some kind of classification results. So the modular space is just going to be vector space of yeah. So, but I'm not. This is more like a Tech-Muller space where I'm not considering then possibly some Fanning group acting on this coming from. Well, no. So if you just, I mean, you expect it to be something kind of Keller if you complexify, right? If you have the moduli of the sort of C fields, then there's a natural sort of Keller potential, that you write, and then people are studying sort of properties of this. But which is yeah. Well, no, here it's all sort of together, right? So, for example, in this direction, sort of one thing that yeah, so for compact manifold, this was the result of Dominic. This is just locally is just the third cohomology of the manifold, or even better is you can locally embed inside H3 plus H4 as a sort of Lagrangian graph. And that sort of projection on H3 is locally an isomorphism. So, so just to follow up on that comment. So for example, here in this theorem, we have these infinitely many G2 metrics that live on circle bundle over asymptotically conical Calabi-Yau. So for example, for this, one thing that we can say is that the moduli space is precisely isomorphic to the moduli space of the asymptotically conical Calabi-Yau metric, subject to this constraint on the Keller class. And when I say moduli of the Calabi-Yau metric, I really mean both Keller and complex structure moduli together. They all become sort of moduli of the G2 metric, sort of indistinguishable. Which one is which? Okay, yeah. Yeah, yeah. And that sort of realized, for example, here. Okay, so last result that I'm going to say, I mean, I'm not sure. Well, I'm not sure if it's interesting at all for you, but sort of mathematically kind of interested is maybe connects to something of the things that Bobby was mentioning yesterday, in the sense he was saying how the only currently known compact simply connected Ricci flat manifolds have special holonomy. And I mean, in the compact case, we don't know non-flat Ricci flat examples, but we don't know whether that's just because they're hard to find or they're not there. Sort of just something even for this kind of non-compact special class of non-compact manifold, we see that there's something kind of more rigid for special holonomy with respect to general Ricci flat. So, and it's the following statement. So, so I could consider situations where at infinity I really have a product, Calabi-Yau cone times a circle, really product. Okay, and then what we prove is that in that case, actually, the G2 metric. If I have a G2 metric that has asymptotic to something like this, then it must actually be Calabi-Yau time product with a circle, right? So possibly modulo some finite group of isometries, and if we move to just Ricci flat non-special holonomy worlds, then there are actually examples that are asymptotic to product cone times a circle, but which are not products manifold times a circle. So, and the simplest one, they're actually very simple. They're just higher dimensional analogs of Euclidean Schwarzschild metric. You can just take any compact Einstein manifold with positive scalar curvature, product with R2, and then you do some word product metric on this. At infinity, this looks like S1 coming from rotation in R2 times the cone over this Einstein, the Ricci flat cone over this manifold. Okay, I'll finish here. Thanks.
Any other questions? Thank you. Do you expect to get the ACG2 metric by bringing epsilon to infinity for other Calabi-Yau base, or
that
or just for some manifold you're not able to bring it to infinity? There will be some obstruction.
I mean, it's not is not clear. So, but I mean, doing that in general would mean sort of being able to say something about kind of the generations of G2 holonomic metric, and we currently don't know. So if you try to deform this, there could be all sorts of singularities deforming, etc. So I mean, it's a difficult question, and I don't think there's any tool at the moment to be able to answer.
So like mostly it will depend on the Calabi-Yau base, like the properties of Calabi-Yau.
It's not clear. It's not clear.
Oh.
I mean, it's just it's not so clear to me.
So for Calabi-Yaus, we have the Picard-Fuchs system to compute the periods of the holomorphic 3 form. Is there anything similar to that we can use in the M3 for G2 manifolds?
I'm not sure. I mean, I honestly declare my ignorance on this. I will be, but.